Welcome to Tomorrow Unveiled, your essential guide to the future being built right now, beyond the headlines.
And what a week to be building.
It really was. This past week wasn't just busy for the space economy. It felt like a fundamental pivot point.
A pivot is a good word for it.
We saw the whole domain move, I think, irrevocably from that sort of conceptual ambition.
And maybe one day talk.
Exactly. I mean, maybe one day we'll have a fully reusable infrastructure idea to something tangible, high stakes, and, well, intensely competitive. It's real now.
Exactly. And what our dedicated research team synthesized for this week, it wasn't just a list of cool launches, it was strategic intelligence.
Right.
The core narrative that we pulled from all the data is profound. Technical capability across propulsion, materials, autonomy, it's soaring. We are seeing generational leaps.
But there's a but.
There's a huge but. At the same time, the global governance, the operational resilience, and the policy architecture you need to handle all this new complexity, it's lagging, dangerously behind.
And that's our mission for Tomorrow Unveiled today. We're going to unpack the most important breakthroughs and news from the space and aerospace domain over the last 7 days. We'll cover everything from who really owns the heavy lift launch market now to these revolutionary AI models that are trying to simulate the entire Earth.
And the immediate multi-trillion-dollar risks. We have to talk about the solar activity.
We absolutely do.
The material we compiled is robust. I mean, it covers everything from commercial finance reports and next-gen engineering documents to NASA's long-term architecture roadmaps.
So we're really defining this new space age.
We are, an age where success depends not just on who has the best tech, but on who can manage the geopolitical competition, the environmental threats, and frankly, the policy.
We are officially moving beyond just dreaming about space.
Oh yeah, we're governing the complex system it's become.
Okay, so let's start with what was arguably the biggest physical milestone of the week. The kind of thing that just redraws the map. The new era of reusable heavy lift. On November 13th, 2025, Blue Origin had the second successful flight of their New Glenn rocket. We knew this was important, but the strategic milestone here was absolute.
It was a complete game changer. The vehicle performed, flawlessly, but the moment that's going to be studied for years in business schools and market analysis offices...
The landing.
The first ever successful landing of that reusable first-stage booster.
Which they so brilliantly named Never Tell Me the Odds.
A great name.
And it landed cleanly on the recovery ship, the Jacqueline. This one event, it changes the entire geometry of the high-value launch market, doesn't it?
It absolutely does. I mean, for the better part of 5 years, the domestic reusable heavy lift market was functionally a monopoly.
Held by one major company we all know who.
Right. The success of the New Glenn landing means that monopoly is officially, functionally over. We have instantaneously moved into a true reusable heavy lift duopoly.
So when that happens, when you get proven competition in a high-value space like this, what's the immediate market impact? Is it a price war, or is it still about who has the best capability?
At first, it's both, but the pressure shifts instantly to price. This success injects intense price and capability competition right into the highest value national contracts.
We're talking about the big stuff.
The biggest. Massive, decades-long programs like NASA's Human Landing System for Artemis and, crucially, the multi-billion-dollar national security space launch manifest for the Department of Defense.
So, okay, does this mean the launch market is now sort of clearly segmented in 3 distinct ways?
That's the perfect way to look at it. You've got your constant, high-cadence utility launches to low Earth orbit, Leo.
Wow.
Then you have the legacy high-value market. They're still using older, non-reusable rockets for those too big to fail classified government assets where, decades of heritage is the top priority.
And now this new category.
And now this new, highly competitive, reusable heavy lift category, and those older legacy providers, they are now facing a genuine existential threat.
Because a new competitor can promise reusability, which means long-term cost savings and also extremely high mission assurance.
It disrupts from the bottom up and the top down. It's a total paradigm shift.
But it wasn't just about the rocket, was it? The payload itself, the Escapade mission, that's a fascinating pathfinder for a whole new way of doing deep space exploration.
It truly is an incredible mission model.
Enabled by these new economics.
Exactly. So ESCAPADE stands for Escape and Plasma Acceleration and Dynamics Explorers.
A mouthful.
A bit of one, yeah. But what it is these are twin probes built fast by a commercial partner for NASA, and the total cost for the whole mission was under $80 million.
Under $80 million.
Yeah. Now, if you put that against the multi-billion-dollar flagship missions we usually see for deep space science, that is a transformative affordability index. It's a different world.
And the operational plan is what really stood out to our research team. They didn't just, fling them straight to Mars. They're taking a detour.
Yes. They demonstrated a new trajectory model that really capitalizes on gravitational stability. The probes were deployed towards Mars, but they're going to wait at a staging point.
The Earth-Moon L2 Lagrange point.
Specifically there, before they make the final closing burn to get to Mars for the actual science mission.
So for our listeners, what makes L2 such a good parking spot? Why not just go straight there?
Well, think of it like a really convenient, low fuel cost parking orbit. Lagrange points are these special spots in space where the gravity of two big things, here the Earth and the Moon, it all balances out the force needed for a small object to just hang out with them.
So it saves a ton of fuel.
A ton of fuel. Waiting at L2 lets the probe keep its position without constantly firing thrusters, saving that precious fuel and operational cost while they wait for the perfect alignment to make that final, efficient push to Mars.
So this is the real core of the new deep space model, then.
I think so.
If you can launch small, cheap probes often and use these powerful, reusable commercial rockets to get them on their way, the whole cadence and the risk tolerance for deep space science changes.
It changes completely. It proves we don't have to put all our scientific eggs into one multi-billion-dollar basket every decade.
Right.
We can now leverage this heavy-lift duopoly to launch, squadrons of small, affordable probes. This drastically increases the cadence of exploration, and it lets scientists take risks they could never, ever justify with a big flagship mission.
It accelerates discovery through rapid iteration.
That's the phrase, rapid iteration in deep space.
And beyond the heavy lift race, our research also flagged some critical refinements happening inside the established government propulsion systems.
Yeah, innovation is happening everywhere. We saw successful validation of the RS-25 engine.
The workhorse for the Artemis program.
The powerful Heritage engine for the Space Launch System, yes. And this was after they incorporated advanced manufacturing techniques.
So 3D printing, basically.
Essentially, yes. The key takeaway here is that the testing confirmed the engine performed perfectly even after they introduced these complex geometries and components made using 3D printing right into its most critical human-rated systems.
And that isn't just some technical achievement. It's an economic lifeline for the long-term sustainability of Artemis.
Absolutely.
Yeah.
Traditionally, making these parts required massive, specialized tooling, long lead times. It drove up the fixed costs like crazy. By using additive manufacturing, you can simplify the supply chain, you rely less on that old tooling, and you dramatically cut the recurring production costs. This is how you make a program like Artemis economically sustainable for decades.
And switching gears globally to sovereign capabilities, we tracked steady progress from India's Gaganyaan human spaceflight mission.
And their focus is all on independence.
Right.
India is laser-focused on indigenous control, supply chain independence for human spaceflight. It's a core part of their Make in India vision. This week, the big news was the delivery of the first human-rated L-110 stage Vikas engine.
So that's the core stage engine for their own rocket.
Yes, this liquid fuel core stage is essential for powering their own human-rated launch vehicle. It shows a really robust state commitment to doing it all themselves.
And crucially, they also confirm safety redundancies. That's always paramount in human spaceflight.
Oh, always. Our research noted a successful worst-case scenario drop test of their crew module's main parachute system.
How do you test for a worst-case scenario?
They intentionally delayed the opening of one of the main parachutes, and the test validated the system's redundancy. It confirmed the capsule can land safely on just 2 of its 3 chutes.
Wow.
That is a crucial step for astronaut safety during re-entry and landing, and it confirms India's status as a really serious contender in the human spaceflight domain.
Okay, so if the first segment was about the physical infrastructure maturing, this next one is about accelerating the future itself.
Pushing the limits.
Pushing the absolute limits of speed and autonomy. We're talking about moving from chemical combustion to nuclear power, and from just processing data to building these revolutionary AI world models.
Let's start with propulsion. The cutting edge.
Hypersonic and nuclear.
The advancements here this week were just stunning. It shows these parallel paths to getting faster. GE Aerospace reported successfully demonstrating 2 advanced rotating detonation combustion engines, RDC.
RDC. It sounds violent, which I guess is part of its power. How does it work differently from, say, the controlled burn of a standard jet or rocket engine?
It totally flips the script on how we use fuel. A standard engine uses deflagration. You can think of that as a smooth, contained fire pushing the air out.
A steady push.
A steady push. RDC, on the other hand, uses the energy from continuous, controlled, super-fast waves of explosions, detonations that travel through the combustion chamber.
So instead of that steady flow of power, you're basically running on a rapid series of controlled shock waves. What's the benefit of that?
Precisely. You're trading a smooth stream for a machine gun of energy.
I like that.
And this process yields far higher thermal efficiency and drastically higher thrust from smaller engine sizes. The vehicle can fly farther, much faster, and often in these unpredictable paths.
Which is key for strategic applications.
Absolutely. This is about making hypersonic vehicles that can fly seamlessly across a whole range of high Mach numbers, which just dramatically compresses an adversary's time and room to maneuver.
So RDC is for speed in the atmosphere. If you want true deep space speed to, say, shorten the trip to Mars, you have to talk about nuclear thermal propulsion, NTP.
And our research highlighted a major theoretical leap here, a next-generation concept called the Centrifugal Nuclear Thermal Rocket, or CNTR.
CNTR.
Right. And this is a technology that could fundamentally change the timeline for crewed missions to Mars. It offers a much-needed solution to the radiation problem.
How transformative are we talking here in terms of performance?
The CNTR concept is highly advanced. It involves spinning liquid uranium fuel in a centrifuge. And that design is intended to roughly double the efficiency, or what we call specific impulse, of earlier solid-core nuclear rocket concepts.
Double the efficiency.
And that performance boost is the central bottleneck we've been trying to solve for deep space travel for decades.
And that increase in performance translates directly into a shorter trip time, which is what really matters for human health on those long journeys.
It does. If they can successfully implement this technology could slash the crewed Mars transit time to about 6 months.
6 months, that's incredible.
And that 6 months is key because it dramatically reduces the crew's exposure to deep space radiation. Radiation exposure is one of the single biggest medical hurdles and operational risks for a crewed Mars mission.
It can cause all sorts of long-term health problems.
Exactly. So cutting the time in half is a profound safety improvement that makes the whole thing much more feasible.
The other major acceleration we saw this week wasn't physical, it was informational. All driven by AI and autonomy. Let's talk about pure speed when it comes to processing the signals coming down from assets in space.
The acceleration here is genuinely revolutionary. New AI systems achieved a colossal 600-fold, that's 600 times, speed increase in detecting and processing faint intermittent signals from space.
600x.
600x. Now, when you consider the vast amounts of telemetry, sensor data, and signals pouring down from orbit, not just communications, but scientific data, warning data, this isn't a minor efficiency gain.
No, that's a different category of improvement.
It's a fundamental change in how quickly we can understand, track, and react to what's happening in the space domain. It could potentially give us near-instantaneous warning of orbital risks.
And this AI efficiency, it's not just helping us track satellites, it's helping us model entire planetary environments.
That's right. Transformer-based machine learning models are accelerating the notoriously slow and complex radiative transfer calculations.
Okay, what are those?
They're essential for accurately modeling a planet's atmosphere, and these new models are accelerating those calculations by orders of magnitude. It means we can simulate and predict atmospheric behavior, whether it's on Earth or Venus or some exoplanet, far faster than we ever could with just traditional physics-based supercomputers alone.
In tying this AI capability back to Earth, we saw more details on the ambitious Earth World Model, the WRW project. This is an attempt to create a total integrated digital twin of our planet.
The WRW project is massive in its scope and its methodology. It involves researchers trying to figure out how multiple distinct AI models—
So an emulator for global climate, an AI for weather forecasting, one for wildfires.
all of them, and trying to couple them together to simulate the entire Earth system, the atmosphere, the water cycle, the land surface, all as one.
But how do you link these separate specialized AI systems so they can actually talk to each other without misunderstanding the science?
The methodology is the key innovation here. They're linking them through what's called their latent spaces.
Latent spaces.
Yeah. Think of the latent space as the AI model's own internal, highly compressed, abstract understanding of reality. It's deep internal knowledge.
So you're connecting their brains, essentially.
That's a good analogy. By sharing those latent spaces, the models establish a kind of universal translator or an internal consensus mechanism. This integrated approach lets them link global climate changes to precise local impacts.
So the prediction from the climate AI won't be inconsistent with the localized weather AI.
Exactly. The idea is to better understand those highly complex, nonlinear interactions between the atmosphere, the water cycle, and the land that are currently hidden from our models.
We want to know how a change in deep ocean currents might, eventually show up as local flooding or specific crop failure somewhere else.
Precisely. This effort is aimed at revealing connections in the climate system we just couldn't see before. It helps us better assess risks and make well-founded, localized decisions for climate adaptation. This technology, if it's successful, is a revolution in complex systems science.
And moving from software to hardware, our research also flagged thermal management as a huge bottleneck for advancing high-performance computing in space.
Oh, it's the absolute limit. Thermal dissipation. Heat.
You can't get rid of the heat fast enough.
Exactly. As your computational density goes up for those 600x faster AI systems we just talked about, the ability to shed heat efficiently becomes the #1 design constraint. If you can't cool it, the system throttles down, or worse, it just fails.
And the industry is responding with major investment in next-gen manufacturing to solve this purely technical problem.
It is. Fabricate Labs secured a massive financial commitment to expand its electrochemical additive manufacturing, or ECAM, capacity in the U.S.
And ECAM is crucial because why?
It offers the precision and the design freedom you need to create these highly optimized, complex heat exchange geometries that are just about impossible to make with traditional methods like milling or casting.
So this is all about creating tiny, complex cooling channels deep inside a super dense computer chip to make sure that the exponential growth in processing power doesn't just lead to thermal failure.
That's it, exactly. This investment secures the domestic supply chain for these specialized, high-density components you need for thermal resilience in space. It's the plumbing required to run the advanced autonomy systems of the future.
And finally, in this realm of advanced materials and in-space biology, we saw developments that sound like they jumped straight out of science fiction.
Yeah, the bioengineering breakthrough was phenomenal. A team successfully 3D printed functional human muscle tissue, they're called myotubes, in simulated microgravity.
And they did this on those parabolic flights, the Vomit comets.
They did. But why is microgravity so essential for something like bioprinting?
I was going to ask.
On Earth, the bioinks, which are these fragile mixtures of living cells and gel scaffolds, they immediately get deformed and collapse under their own weight because of gravity. It makes it impossible to print complex, three-dimensional structures. Microgravity removes that constraint. So this proof of concept shows that functional human tissues, and the hope is one day entire organs, might be manufactured in orbital biofabrication labs.
Using the space environment to overcome our terrestrial limits.
For long-duration missions and maybe even for use back on Earth.
And to help the human components that are already heading to the Moon and Mars, we saw a glimpse of some enhanced astronaut mobility systems.
Yes, a prototype wearable exosuit with artificial muscle actuators was unveiled. It's designed to be worn under the standard EVA suit.
So it's not a new suit, it's an undersuit.
It's an undersuit. It uses fabric-embedded robotic muscles to augment the astronaut's own strength, reduce fatigue, and make bending or doing heavy labor easier. Given how bulky and stiff the current EVA suits are, this could be a major breakthrough for astronaut endurance and effectiveness on the surface.
Now we move to the foundational strategy that really dictates much of the commercial and technical development we just discussed. Laying the foundations for Mars through the Moon to Mars architecture.
And this past week gave us tangible proof that the cislunar supply chain is maturing beyond just being a concept on a PowerPoint slide.
What was the proof?
The successful shipment of the 4th European Service Module, the ESM-4, for the Artemis the 4th mission, it arrived at Kennedy Space Center.
So the hardware is on the ground.
The delivery of this complex, long-led international hardware confirms the irreversible commitment to and the maturation of the cislunar supply chain. It's not theoretical anymore. The physical parts are arriving.
And for listeners who might not be familiar, what exactly does the European Service Module do? It's much more than just a propulsion unit for the Orion capsule.
Oh, it is the absolute powerhouse and lifeblood of Orion. The ESM provides 11.2 kilowatts of electricity.
Which is a lot.
It's more than enough for 2 average 4-person households. It also provides crucial propulsion via 33 different engines.
Including a repurposed shuttle engine, right?
Yes, the main engine is a flight-proven, repurposed Space Shuttle Orbital Maneuvering System engine. It provides critical life support, temperature regulation, and autonomous control for things like tracking the sun with the solar wings. It's the core infrastructural link in the deep space chain.
And Artemis IV is the mission that's slated to really start building out the critical orbital platform, the Gateway.
Correct. The Gateway is no longer a concept. It is now an asset under verifiable construction.
Yeah, right.
And our research team highlighted that this forces a major strategic pivot for the whole domain. The lunar economy is transitioning from being an access economy, just focused on getting there with rockets, to an infrastructure utilization economy.
Focused on actually using the assets we're now building in orbit.
Exactly. And logistics are the key to using that infrastructure efficiently.
Deep space logistics, DSL.
That's the commercial mechanism. They'll rely on commercial providers to transport critical pressurized and unpressurized cargo everything, from food and spare parts to science payloads, up to the Gateway.
Which is what you need to maximize how long the crew can stay and what they can do there. And, if you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future. So let's zoom out now and look at the overarching philosophy behind this entire Moon to Mars plan. It's a very specific, strategic way of thinking that guides all these efforts.
Yeah, the foundational philosophy is captured by 2 complementary systems engineering principles: architecting from the right and executing from the left.
Okay, explain that. It sounds like pure systems engineering jargon, but you're saying it's the engine room of the whole strategy.
It really is. Architecting from the right means you start with the long-term, ultimate goal-sustained human presence on Mars. That's the furthest point to the right on your timeline.
And you work backward.
You work backward from there, you figure out all the requirements, the systems, the technologies you need for Martian success, and then you figure out how to build them.
Okay, so what's executing from the left?
Executing from the left means you implement those systems in achievable, affordable phases, starting with the most immediate segment, which is human lunar return.
You build the minimum viable product first.
You build the MVP first, but always with the knowledge of where you must eventually end up.
And this methodology, it dictates the 4 major segments of the whole progression. Can you walk us through those 4 segments, explaining the goal of each phase, starting with where we are today?
Sure. The first segment is human lunar return, or HLR. This covers the initial sortie missions, Artemis I, II, and III. It's about establishing the core capabilities.
Orion, the SLS, the first human landing system, the first bits of Gateway.
Exactly. The focus here is on human-conducted science, crew training, sample collection, essentially proving we can get there reliably again.
Then what's the next step up to foundational exploration?
Foundational exploration, or FE, expands the operations dramatically. We move to longer crew durations, regional exploration focused specifically on the lunar South Pole, and increased mobility.
And this is where the Moon becomes a testbed for Mars.
Critically, yes. Missions in this phase act as Mars-forward precursor missions. They test the systems like pressurized rovers and advanced habitats that are required for Mars risk reduction, using the Moon as the ideal, closer proving ground.
And that leads naturally into the third stage, which is more focused on industrialization.
Sustained lunar evolution, or SLE. This is about growth to support global utilization, economic opportunity, and a steady cadence of human presence.
This is where we start using local resources.
The technological focus shifts strongly toward industrial power generation and in-situ resource utilization, ISRU, using local resources like water ice for propellant, oxygen, life support. This is where the lunar outpost becomes a sustainable industrial base.
And all of that finally informs the last segment. Humans to Mars.
The final segment. It captures the initial capabilities, systems, and operations you need to establish human presence on Mars, relying entirely on the knowledge, the systems, and the resilience you validated during that SLE phase on the Moon. You only make the ultimate leap once you've proven the infrastructure closer to home.
And when planning for Mars specifically, the sheer complexity is just immense. It's defined by 6 fundamental questions that decision-makers have to balance.
It's the six-sided trade space of Mars architecture. Who goes, what they do, where they land, when they leave, how they get there, and why they're even going.
And the difficulty is that the answer to any one of those questions heavily influences all the others.
Oh, completely. You change the crew size, the who, and you dramatically change the propellant mass, the how, and the mission duration, the when.
And our research highlighted a classic, very expensive example of prioritizing one of those questions over the others. The Apollo program. What's the cautionary tale there?
The Apollo program prioritized when. The explicit mandate was to land a man on the moon and return him safely to Earth before the end of the decade.
A hard deadline.
A very hard deadline. And it resulted in an architecture that was fantastically successful for that immediate goal, but it was optimized entirely for schedule, not for extensibility.
It was hard to evolve those systems for long-term sustainable operations.
Exactly. And that serves as a stark warning for Mars planners. If you prioritize when above all else, you risk building an architecture that isn't affordable or adaptable for the multi-decadal goal of permanent presence.
And the difference in just the physical scale between a moon mission and a Mars mission dictates massive compromises in the architecture.
The scale is immense. A single round-trip journey between Earth and Mars travels up to 2 billion kilometers.
2 billion.
That's roughly 950 round trips to the moon. The physics are just fundamentally different, and that dictates all your energy trade-offs.
Let's discuss that energy trade-off then. Short trips versus long trips.
The total mission duration is the primary driver for all your propulsion decisions. Longer missions, around 3 years total, what we call conjunction class, they require lower energy because they rely on more favorable, efficient planetary alignments.
But 3 years is a long time to be in space.
It's a very long time. Shorter missions, around 2 years, or opposition class, require exponentially more energy and propulsion to fight against the natural orbital mechanics. But critically, shorter missions reduce the medical risk for the crew.
So it's a direct, painful trade-off between massive amounts of propellant and the health of your crew.
A painful trade-off. And something like that CNTR, nuclear propulsion we talked about, is what attempts to break that trade-off.
And finally, you have the critical decisions on crew protection and life support once they actually get to the Martian surface.
Key decision points for Mars surface systems include minimizing crew size. The current practical minimum is assumed to be 2 for safety and managing the whole ingress and egress strategy.
Getting in and out of the habitat.
Right. Planners have to decide on airlocks, hatches, suit ports, all while mitigating the pervasive, corrosive Martian dust problem and adhering to strict planetary protection requirements.
And there's a profound policy assumption about that Martian dust, specifically the issue of backward contamination, bringing Mars stuff back to Earth.
Yes. This is a crucial policy detail our research highlighted. Current operational concepts assume the Mars EVA surface suits, which will be heavily contaminated by Mars dust,
Yes.
will be left behind on Mars.
Wow.
Crew members would return to Mars orbit in their clean intravehicular activity, or IVA, suits, breaking that chain of potential backward contamination before they start the journey back to Earth.
That's a huge decision about what we bring back and what we permanently leave behind. All right, moving on to our final segment, let's address the strategic challenges that are threatening to slow down or even derail this incredible technological progress.
Orbital geopolitics and systemic risk.
We have to start with the geopolitical race for orbital scale, which is really being led by China.
The strategic news on launch cadence this week confirms a structural tipping point in global space competition. China successfully exceeded its previous annual orbital launch record. They're on track to hit 70 to 72 missions for 2025.
Okay, now wait a minute. U.S. commercial launch, which is primarily driven by one provider, is still significantly higher, well over 150 missions this year. So why should we care if China only hit 70?
That 70 is strategically crucial because of what it signals. It signals a decisive shift. The competition has moved from isolated tech superiority to efficient mass production and rapid state-driven deployment.
So it's about manufacturing scale.
China views manufacturing and deployment scale as a primary strategic asset. While the U.S. cadence is higher, it's commercially decentralized. China's increase confirms they can rapidly build out government-controlled mega-constellations intended to rival Western systems at an industrial scale.
It's the weaponization of manufacturing capacity.
That's a very good way to put it.
And this scaling isn't just confined to the legacy space powers. We're seeing a global proliferation among, middle powers using this sovereign-in-a-box model.
Our research highlighted the establishment of the OrbitWorks facility in Abu Dhabi as the perfect archetype of this trend.
Right.
This facility is essentially a ready-made industrial base. It's enabling regional powers like the UAE to rapidly become regional producers and eventual exporters of space tech, rather than just being passive customers who rely on the West.
And this industrial proliferation, it just further fragments the global space order and intensifies competition for orbital slots and frequency allocations.
It does. And while launches are accelerating globally, in-orbit logistics are still pretty nascent. However, there's a new regulatory driver pushing in-orbit servicing, or IOS, forward. It pretty much guarantees its necessity.
Okay, what is that?
IOS, which includes upgrades, life extension, and critical debris removal services, is rapidly transforming from being an optional premium service into a responsible space operations regulatory imperative.
And this is being driven entirely by the growing requirements for orbital debris mitigation.
Exactly. Evolving national and international regulations about debris and the lifespan of satellites mean that operators who proactively incorporate iOS solutions into their business plan gain huge compliance advantages and lower their long-term liability.
So the regulations are creating a market.
This external regulatory pressure guarantees a sustainable commercial market for in-orbit logistics providers. It effectively de-risks the massive capital investment required to scale up orbital refueling and servicing infrastructure.
Okay. Shifting to a non-geopolitical but equally serious risk, the unseen threat of extreme space weather. And this past week gave us a very tangible, real-world example of its operational impact.
It did. We saw the immediate consequences of an X5.1 solar flare and the G4, G5 geomagnetic storms that followed, and the impact was concrete and immediate.
The New Glenn launch.
The Blue Origin New Glenn launch, carrying those sensitive Escapade Mars probes we discussed earlier, had to be scrubbed.
Which confirms space weather is a core scheduling vulnerability, especially for planetary missions that have these very precise launch windows that only open up every few years.
Absolutely. That delay caused immediate cost overruns, and more importantly, it underscored that your mission execution now hinges on predicting and hardening your systems against these solar events.
And the authorities issued strong warnings.
They did. The British Geological Survey and others issued warnings about expected disruptions to both orbital and ground-based technologies, specifically citing impacts on power grids, communication systems, and GPS accuracy.
And the financial systemic exposure is what really makes this a global risk, not just a space risk. How much are we talking about here?
The leading insurance markets have modeled the financial fallout of an extreme solar storm, and they're projecting potential global economic losses ranging from $1.2 trillion up to a devastating $9.1 trillion over a 5-year period in the most extreme scenarios.
$9.1 trillion. That's just staggering.
That mad bug.
And that loss, it's not primarily about fried satellites, is it? It's about the infrastructure on the ground.
Precisely. The majority of that loss is driven by damage to critical terrestrial infrastructure. Electric power grids, satellite communications networks, and the global navigation satellite systems like GPS that underpin vast segments of our global economy.
Everything from finance to agriculture.
All of it. This cements space weather as a critical factor for global financial stability, and it requires mandated resiliency across multiple industrial sectors.
Now let's talk about a risk the U.S. space economy is largely inflicting on itself, the policy and regulatory paradox. First, the Space Traffic Management, or STM, vacuum.
A risk report highlighted the precarious future of the U.S. Office of Space Commerce, or OSC. Now, this is the office tasked with developing the Civil Space Traffic Management System, CSS.
And that's supposed to take over collision avoidance warnings for all non-military satellites from the Department of Defense, which is just completely overburdened.
Exactly. And the paradox here is the proposed defunding of this office.
Right when we need it most.
Yes. The proposed defunding creates a dangerous vacuum in space governance precisely when commercial space traffic is exploding exponentially. Experts called this strategic dissonance.
The commercial side is dominating, but the government isn't providing the public infrastructure to support it safely.
Right. If the OSC is hobbled, it forces a dangerous reliance on military systems for civil functions, and it just increases the risk of collision in orbit.
And the second self-inflicted wound is the Cybersecurity Compliance Barrier, CMMC.
The U.S. DoD's Cybersecurity Maturity Model Certification Program. It's now in force, and it's strategically necessary to protect the defense supply chain from cyber threats.
So it ends the era of self-attestation for cybersecurity. Can't just say you're secure anymore.
You need third-party audits. And that sounds like necessary diligence, but what's the negative consequence for the market?
The cost.
The compliance is a massive costly burden. Large prime contractors can absorb the cost of mandatory third-party audits, the software, everything. But the small, agile, innovative new space companies and startups,
The source of all the disruptive innovation.
right, they often cannot afford the multi-year compliance complexity and the mandatory audits, which can cost tens or even hundreds of thousands of dollars.
So the unintended consequence of this necessary strong regulation is it consolidates the market and it risks U.S. innovation speed.
Exactly. It risks slowing the pace of U.S. innovation relative to its adversaries by forcing smaller, innovative companies to either get acquired by larger primes who can handle the compliance or just exit the defense market entirely. It's a significant strategic drag.
Finally, we need to address the urgent discussion around the rescue gap for astronauts. This has been called a massive wake-up call.
Following recent incidents like the Chinese crew's extended mission wait due to a vehicle issue, experts have highlighted that those situations involved crew members who could rely on space stations as temporary safe havens.
That's the critical distinction.
And that contingency plan disappears once we've entered deeper into space.
It does.
Current contingencies rely on space stations, which can temporarily house a stranded crew. But this is not a viable strategy for free-flying deep space missions, particularly as we push toward Gateway and Mars, where there is no permanent safe haven.
So what's the solution?
There isn't one yet. There's currently no dedicated high-readiness space rescue capability or international consortium. It's a massive gap that needs to be addressed immediately before the next incident occurs far beyond low Earth orbit.
If you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners.
It really does.
And we love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the escalating geopolitical race for manufacturing scale in space. So what does this all mean? As we close out this deep dive on Tomorrow Unveiled, we are left with a clear and a really striking dichotomy defining the space sector this week.
On one side, you have these just stunning efficiency gains. RDC pushing the speed barrier, AI accelerating data processing 600-fold, reusability moving from a monopoly to a duopoly.
The physical and digital tools we need for sustained human expansion are maturing faster than anyone expected. It's making Mars feel feasible within our lifetime.
But those gains are completely juxtaposed against profound accelerating risks.
The geopolitical race for orbital scale, the tangible and massive financial threats from solar storms that dwarf any space budget, and the policy vacuum being created by regulatory stumbles right here at home.
The final synthesis is clear. Sustainable growth beyond Earth requires the systematic, mandated integration of innovation with operational resilience.
It's not just about who has the fastest rocket anymore.
The future of the space economy depends not just on who can build the fastest, most efficient rocket, but who can best manage the collective risks inherent in a crowded orbit and a geophysically volatile solar system, and who can build the governmental structure to keep it safe.
And that leaves us with a provocative final thought, directly related to that massive scientific undertaking we discussed, the effort to model our home planet. If we successfully build a perfect digital twin of the entire Earth system using AI, leveraging that unparalleled predictive capability to reveal hidden connections in the climate, will we use that powerful knowledge primarily to save the complex system we have?
Or merely accelerate our departure to the next one?
That is the question.
And one we will continue to track here on Tomorrow Unveiled.
Thank you for joining us for this deep dive on Tomorrow Unveiled. We'll see you next week as Tomorrow Unveiled continues to explore the future.